Here, I sent an email out about the textbooks or the notes still being out in the bookstore. Some of you, how many of you are still waiting to buy them? Maybe count 1, 2, 3, 4. He says maybe.
Well, I bought it, but it hadn't come in yet.
Oh, okay, so you still don't have a copy yet. Okay, that's why you were so like, how is that yes or no? I'll give you credit for that. 5, 6, 7, 8 of you at least. Okay, so they're ordering more. They're coming in. I think the answer's tomorrow. But
I
yeah.
called yesterday and they said, oh, we're putting them as we speak. And so I went over there like, oh, it should be ready.
So maybe it's today. So actually, I think it was tomorrow, but that was yesterday. The guy who prints them wasn't there, was the problem. But now he's back. They're supposed to be in soon. But the problem is they're not sending any here. You all read my email about that? So if your only option is to go to Pittsburgh and buy one, or order it online, they'll send it to your house. I wanted to make sure I knew how many were in our class, because they're printing more for some other classes as well. And if we have 8, we can assume maybe every other class has about the same amount, so we can estimate how many more they need to print, because I'm not sure they're printing enough. So for those of you who didn't get that yet, I have the notes for today, for those 8 of you. Show me your hands again, I should have done this all the same. We're starting today on page 20. What I just passed out to those of you who don't have them yet is 20 and 24, because those are actually the only 2 pages of notes we're taking today. Everyone okay with the notes? All right. Now remember all the corrections you were making in the note packet. We already replaced one lab assignment last time. I have another one for you to replace. This is for all of you. We're replacing pages 22 and 23. So this paper will replace 22 and 23. Graphs, we did histograms last time. Chapter 2 is about visually looking at your data. So the rest of chapter 2 today is going to be a few different types of graphs. And then we're going to do a little bit of chapter 3, the first section of chapter 3 after the break, which is then calculating some numerical descriptions. Announcement I forgot to write up here. Bring your stats calculator on Monday. If you don't have one yet, you could buy one between now and Monday. I can talk and spell at the same time, that'd be great. You can check one out in the math lab with a photo ID. Or if you fall into one of the many categories that I listed on the first day, if you don't remember what they are, there's a sign in the math lab that tells you you may be able to still check one out for the whole semester. If you haven't already done that though, they may have already given those all out. But there are some options. But we will be using it, and your life will be much more challenging if you don't have it. The very first day that we do this in class, I usually bring in some calculators from the math lab with me, but I still have to trade you an ID for the calculator. So if you don't have a chance to get to the math lab before class, at least bring an ID, but there may not be enough for everybody. So if you bring your own, you'll be better off. Okay? So that's all of chapter 3 on. We're getting our calculators. Thank you for passing that over. The black shirt there. There you go. Thanks. All right, so starting on 2.4. This is the list of data that you have on the top of page 20. I just had to write it in 2 lines because I couldn't fit it up here. I just wanted to make sure I had it to point at it. So there's some numbers there. Maybe they are ages. Maybe a bunch of people at a family reunion. That would make sense, right? If we have ages between, what's the smallest one? 6? What's the biggest one? 70? Yeah, I mean, that could be people at a family reunion between ages 6 and 70. A bunch of ages. So that's just a long list of numbers. If I asked you some questions about it, like, are there more younger people or older people? Is it evenly spread out from young people to old people? Is there any group that there's more of or less? I could ask you all these questions, and it'd be a little hard to answer the way it's just written there in the list. Well, let me start counting. I mean, the first thing you might want to do if I ask those questions might be to rearrange them. That's what a stem plot does. A stem plot is the first thing we're going to do. It rearranges the data, it puts them in order nicely, and even tells you about the distribution. Maybe it's distributed normally. We'll see that. So we're going to make a stem plot. There's 2 vertical lines on your paper. The second one's actually going to be our stem plot. The first one is what I call my scratch paper to get started for my stem plot. Your stem plot takes numbers and breaks them into separate digits. In this case, these numbers all have 1 digit or 2 digits. They have to all be the same. Like they have to either all be 2 or all be 1 for us to compare them. But I'd argue that we could write, for example, 9 as a 2-digit number. If we wanted to, what would it look like? 09, right? So we could make this, I mean, we don't usually write it that way, but if we had to make it a 2-digit number, we could. Kind of like if you're doing like the pennies part of when you buy something, right? You can put .09, right? Same idea. So then we could write them all as 2-digit numbers. If they were, can you pull that door shut, please?
Yeah.
Thank you. If they were all, say, if any of them were 3-digit numbers, we'd have to write them all as 3-digit numbers. So that would be 009 or something like that. So they'd have to all match. And then we say, okay, we separate the last digit. There's 1 digit at the end, which means they all have 1 digit at the beginning. Just looking at the first digits, what are my first digits? What's the lowest first digit and the highest first digit in this list? What's the second digit, the first digit? 0. And, sorry?
7.
7? Yeah, because I've got things from 1-digit numbers up to, I think 70 is my highest. So the first digits are going to come over here. They call it a stem plot. This side they call the stems, and this side they call the leaves. Some people call it a stem and leaf plot. So my stems are the first digits. 0, 1, 2, 3, 4, 5, 6, 7. It doesn't matter if I don't have one of each of these. I have to have everything from the smallest to the biggest represented here. So if I didn't have, say, anybody in the 50s, I think I do, but if I didn't have anyone in the 50s, I still would have to list the 5 here, because these have to be evenly spaced. Everyone all right where those ones came from? So the stems are the first digits in this example. And so now I'm going to easily organize these into groups. I'm going to put them in the right places. So this 9 we said was a 09. So it goes with the 0, so I'm going to put the 9 here. It goes with this guy. The 15 is a 1 and a 5, so the 1 here and the 5 goes here. The next one's a 25, so that goes with the 2 and then the 5. Everyone all right how I know where to put these? Yes.
The 6 need to go before the 9.
I'm not there yet, but it will, yes. The answer is yes, but I'm not there yet. 47. So right now I'm just going across my list, putting the leaves on my plot here, next to the correct stems.
Wait, why did you skip the 3?
I'm just putting each of these numbers. That's actually why I listed them, to make sure I didn't forget any of them. So I've now put those numbers up there. So it's not that I skipped the 3, I'm just putting my list onto this chart. I'm glad you asked though. Other questions on how I'm putting this there? Yes.
How did 16 on there? Because are you on the
Aha, he wants to know what to do with the 16. That's exactly where we are. Wait a minute, we already have a 5 there. You might have a long list of numbers on this 1 digit. So he wants to know how do we put the 16? There's already a 5 here. We just put the 6 right next to it.
Whoa.
I know, well, no commas, just right next to it, kind of evenly spaced, kind of think of these as columns. So this tells me, if I hadn't looked up here, this tells me there's a 15 and a 16 in my list. Same thing with the 6, right? The 6 is a 06, so I would just put it over here. You want to make sure you evenly space these when you put them in there. You don't want to squish some of them together and spread some out. I'll talk about why in a few minutes. So there's the 6. The 28 would go here. I want to make sure I don't lose my place because I keep stopping to talk. Other questions on how I'm putting those on there? Make sure you ask me a question now because I'm about to have you finish it. Everyone knows how to put the rest of those numbers on here.
Well, what about the 32? Would you put it in the first column?
Yes. So everyone hear her question? The 32 is the first one that goes with the 3. So you always start on the left and just keep filling them in as you go. So the 32 will go there. They only just keep moving over columns if you have more of them. So do me a favor. See if you can put the rest of them on there. You're done already? That's what happens. I start talking and people are like, I'm already done, Jill. Some people were listening though and not writing. For those of you who we're not done yet, see if you can fit all those numbers on there. While you're doing that, I'm going to put them on here real quick, and we'll see if we agree. hopefully I copied the list down right. We'll find out if my list doesn't agree with yours here. Does that agree with yours? You could have made a mistake, so if yours is different than mine, just let me know. So we got? So this kind of tells me a lot of information already. This tells me right now I've got 5 numbers that are, 5 people who are under the age of 10, if they're ages, right? I've got 2 people that are in their teens, 2 teenagers, 4 people in their 20s. I have just as many people in my 40s as I do that are under 10, because I have 5 people in this list and 5 people in this list, which is why you want to keep them evenly spaced so you can tell when they're the same length. So here's the bad news. That's not a stem plot. It's almost a stem plot, which is what Christiana's question was about. To be a stem plot, it's almost like this, except your leaves have to be in order. So that's why I gave you 2 lines here. This is my scratch paper to get started. Now I'm just going to come over here, recopy my stems, and then put each row in order from smallest to biggest. If you can do that all in one step, good for you. But it's hard to find the smallest one, then you have to move things over if you miss it. So for me, it's actually easier to make one here and then reorder it to get to my answer. So I'm going to put these in order from smallest to biggest. 6, 6, 6, 7, 9. 1, 5, 8, 8. Putting 2 or 3 numbers in order is a lot easier than putting 22 numbers in order. 0, 1. And these were all in order already. So this guy, right here, is my stem plot. It has the stems, it has the leaves, everything's in order. Questions on that? Here's what we love about stem plots. Number 1, it takes a long list of data and puts it into a nice compact space. If I give you one of these, big hint, on the next test, if I give you a stem plot and say what numbers are listed in this table, could you tell me? If you didn't know what they look like up here, could you read it off of here?
Yeah.
Yeah, right? This one represents a 40 and a 41 and a 45. So you could take them off. So it's all the numbers in a nice compact space. If I asked you for the smallest number, could you find it? Sure, it's right there at the top, right? The biggest number, you could find it. And you don't have to search and like, oh wait, I missed one. There's another one bigger or smaller. The longer the list, the harder it is to find things like that in there. Could you find the one right in the middle? Right in the middle? You had to? How would we find the one right in the middle?
Tell me.
Yeah?
Could you like add like the smallest number and biggest number and divide by 2? Do like an average?
That's kind of an average, but if I actually wanted the exact number that was in the middle of all these, if I had, so that's a good estimate though, I like your idea. But there might be a number like right in the middle, where half people are younger and half people are older. Yes?
Maybe if you go up to the middle column, like go to the 4 and then go to the middle number in the 4.
Okay, so
45.
maybe like the 45? So I like our thinking. Is that the middle? How many people are older than 45? 1, 2, 3, 4, 5, 6. How many are younger than 45? A lot more than 6. I like thinking out loud's good though. Yes?
You could just count from the top and the bottom, maybe. You know?
We could count from the top and bottom until they meet. We could count how many there are and just take half of it. Turns out there's 22 if you count them. So if I counted from the top and the bottom, I'd go 11 down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 11 right there from the top. If I did 11 from the bottom, I'd be, so this is 11 from the top. This is 11 from the bottom. If I went backwards, right?
So what did you say?
What'd you say? I didn't hear you. Never mind. She was thinking but then didn't like it. Say it again?
Between 28 and 32.
It's between 28 and 32. which I think is what you said, she didn't trust herself. We don't have one number right in the middle. But do we agree that half the people are 28 and younger, and half the people are 32 and older? So halfway between those would be 30? So 30 would be the number that half the people are younger and half the people are older. We're gonna learn that later, it's called the median. It's actually a chapter 3 terminology. But because they're in order here, we can actually even find that. Where if I had just given you this list and said, hey, figure out what number is exactly the one that half the people are older and half are younger, good luck finding it looking at this list. I don't know if I would have come up with 30 looking at it. So this organizes it a lot. Here's the other thing it does. Imagine that these little leaves here are bars. Imagine they're bars, like in a bar graph. And then, turn your head sideways and look at it like this. What's it look like? Looks like a histogram, right? It's actually a histogram. It's telling me how many people are in each class. The classes are everybody from 0 to 9 years old, everybody from 10 to 19 years old. It's really making a histogram to go with a frequency distribution. So it's putting it all together in one little place. So I could turn my head sideways like this and ask if it was a normal distribution. No, why not?
It's not symmetrical.
It's not symmetrical. Why else is it not normal?
Skew to left.
Yeah, it doesn't go to like the highest point in the middle. Remember, it's supposed to go up in the middle and then back down. It kind of starts high, goes down, back up again. If this one was shorter and then went up and back down, it'd be closer to normal. So there's a lot of information we can get just by looking at this graph here. Questions about stem plots? You'll be asked to make stem plots on your homework. You'll be asked to interpret stem plots, take the numbers back off, things like that. They're not all this easy, unfortunately. What if I had some weights of some really lightweight pieces of paper, maybe? Who knows how much a piece of paper weighs? And so I had, one that was 0.158 ounces and one that was 0.159 ounces and a 147 and a 163. I'll just stop there for now. So these are some really lightweight, number of pounds or something, some really lightweight things. And they're measured like this, and obviously it would be a longer list if I'm making a stem plot, but I just want to use a couple. If it's not on your notes, I just gave you some new ones. How would we make a stem plot for this? Yes?
Stems would be 0.15, 0.14, and 0.13. I'm sorry, 0.16.
Okay, so the stems, he wants to use the first two digits, 0.14, 0.15, and 0.16. So in our example, the stems were 1 digit and the leaves were 1 digit. The leaves are always 1 digit, so he's totally right. The leaves are always 1 digit. The stems are however many digits you have before that last one. So if even these were 4-digit numbers, the 1 would be the end and my stems would be everything in the front. Imagine you just cut off that last digit here. Right? We just cut off the last digit. Then those first numbers are your stems. And here's what it would look like if I squeeze a little miniature stem plot that's in your notes somewhere or on a new piece of paper. It's little tiny ones, just a couple numbers. Just want to make my point. Notice I didn't put the decimal on there. I'm ignoring the decimals for the moment. We agreed if you forget the decimals, those are my stems. And then I would put those numbers on there. I think I could even put them in order. They're already listed in order, that's good. It would look like this. I agree the decimals are missing. If you didn't know the original numbers, you would just think that's 147, right? So usually when we have decimals, they don't actually go in the plot. What we do is we go ahead and make a stem plot, and then there's a little, what we call a legend at the bottom, where it would say 14/7 represents, represents 0.147. So you just have one little piece of information, and then it's assuming that the reader will know that if that's 0.147, the decimal goes there for all of them. So usually you'll have this little table, the stem plot, along with this little legend down here at the bottom that tells the reader how to interpret it. You're not gonna see a whole bunch of those. Every once in a while they show up, people panic. Don't assume they're whole numbers unless there's no legend. If I hadn't written this, then we're gonna assume those are whole numbers, but there might be something to tell you there's decimals. Okay, with stem plots? Yes.
So what happens if the number is like 1.4, like at the point in the middle?
Ah, so like if my original list was say 1.4, 1.8, 2.9, like that?
Yeah.
Good question. So in this case, I'm making an even shorter stem plot now. What are my stems? Just ones and twos.
Kind of right in the middle.
So ones and twos. And then I would put my leaves over here. And then underneath it, I would write 1/4 represents 1.4. Which tells the reader, oh, that's where the decimal goes for this problem. It goes between them. So as long as you do it for one of them, then we know where to put it for all of them. Good questions. Other questions about stem plots? You'll be given a long list of numbers and asked to make a stem plot. You'll be given a stem plot, asked to interpret it. Yes?
So say it doesn't start at like 0 or 1, can you start at like 3?
Oh yes, start at your lowest stem and then go to your highest. So let's say we had numbers that only went from 30 to 80. You start with 3 as your lowest stem and 8 would be your highest stem. So you don't have to start at 0, but you do have to have every space from your lowest to your highest. If my numbers were only 30s and 80s, I've got a 32, a 35, an 81, and an 86. That's all I have. I still would need to have every stem from 3 to 8. Because remember, it's classes, like the histograms we were doing. Sometimes you had a bar with nothing in it. So then we would put our numbers here and down here. If you thought about it as a histogram, these are classes that all had 0 in them. So you would have to leave some spaces between, but you don't need to go below this or above your minimum and your maximum. Good questions. Other questions? I think we can make a stem plot, interpret stem plots. It won't kill us. It might, it'll be good for you. Okay, next we're going to make a pie chart and something called a Pareto chart, which is not on your notes. First I want to fill in this chart that we already did last time. We talked about candy last time. We talked about candy a lot in this class. I love candy. We'll add Tootsie Rolls to my next one, I decided. That's my current candy of choice, is Tootsie Rolls. It changes all the time. Can someone tell me what the frequencies were in that chart?
7,
7.
11, 14, 7, 0.
So we filled those in last time, and then we did the relative as well. Could you give me those two, please?
Yeah. It was 17.9, 28.2, 35.9, 17.9, and 0.
So this is a little review, what we did last time. This was plain peanut. I'm just putting this here so I don't forget which one is what. Skittles, Reese's Pieces, and none. Okay. So we did this last time. We filled in our frequency distribution. We figured out the relative frequency to make this beautiful table here. So I just recreated on this side because we're going to use it for reference, really. So we want to make a pie chart to go with this information. A pie chart. So I give you a circle there. I'm going to try to draw a bigger one so I can talk about how to make a pie chart. What's funny is a lot of us can read pie charts much easier than we can create pie charts. So I need to make pieces of this pie that represent my 5 categories here.
I think you should start with the 35.9.
She wants me to start with the 35.9. Why do you think I should start with that?
Well, because, 30 is like, it's kind of like a third, like 33 is usually generally like a third.
Okay.
So we know it's just a little bit more, so we divide it into thirds.
Okay, you agree with what she's saying? She wants me to start with the 35.9. I think also because it's the biggest, it's easier to visualize how big it is. And in her head, she's going, that's a little more than a third. 33% is a third. This is a little more than a third. So she wants to visually take this circle and carve out a little more than a third. I completely agree with her approach. If it wasn't that one, I might have started with this one, 'cause it's a little more than a quarter. I mean, however way you want to look at it, it'd be the same idea, right? So a third. So then you have to first kind of visually try to divide this into thirds. Very lightly with your pencil in case you don't agree with your assessment. Try to, pretend mine's a perfect circle, by the way. Does that look roughly like the thirds? Or is that big one on the top too big? If it doesn't look like thirds, I'll just erase it and fix it. I mean, we use
I'll
pencil.
just keep the top one, because even if it is a little bit bigger.
Oh, that's a good
that
point.
doesn't actually change bigger anyway.
These look pretty close to thirds, but in my mind, that one looks a little bit too big. We agree? If it's a little bit too big, that's okay, because we're going bigger than a third, she says. Smart thinking. If you make a mistake, run with it. So because this looks a little more than a third, maybe it is close to 36. So what I would do is take that piece right here. This is the center of my circle. I'll leave that one here, mark that here. And then I would say that this one is 35.9% Skittles. So that's a good start. We maybe need to make it a little bigger, but we're pretty close. When we're done, I'll talk about how I will grade your pie charts, because freehanding them like this is very hard to make them exact. But as long as they make sense relative to everything else on there, we'll be okay. So the next biggest one is 28.2. That's a little less than a third. This little third here was kind of small to begin with. So maybe I'll just cut him down even a little bit smaller. Make it a little bit smaller over here. Again, I'm just eyeballing. I don't want to go that small. Why not? I just realized when I looked at it. Think about a quarter. How much is a quarter?
Half of a half.
Half of a half. What percent is a quarter? 25%? Doesn't this not even look like a quarter of my circle? Doesn't it look smaller than a quarter? This piece right here? So I might have made it too small. I don't want to go lower than 25. I'm trying to go to 28. Again, it depends on where you drew your lines too. I need something smaller than this one, but bigger than a quarter. So I might just move that line out a little bit more. Again, because I freehand it and mine's not even actually a circle, it's a little bit tough. Maybe I'll put dots in here for this one. I think that's pretty good. This one is 28.2% peanut M&Ms. Those of you who like colored pencils and pens, you can make them as beautiful as you want. By the way, when we go to do these in our projects, you can find, I don't know, countless programs online where you just put your numbers in there and it makes you your own beautiful pie chart. You cut and paste. We like that. So there's that. What's my next one? 17.9 and 17.9. What are you going to tell me about both those pieces? They better be the same size. And those are all I have left, because the last one is 0. So what am I going to do with this last piece right here? Just cut it in half. Here's my green. I'm just going to cut it in half. This is a really sloppy circle. Just saying. Cut that one in half. Maybe I'll put vertical stripes in this one. This is 17.9% plain M&Ms. And I'll just leave this one white. 17.9% Reese's Pieces. I don't have to mark that there's none on here. It's obvious there's none on there. So this takes, everybody chose these 4 categories. There is nobody in the none category. What would I have done if, say, one of these was, like 8%, a really tiny percent? It was 8. How would I have fit that on there?
Somewhere between the 28.2 and the 35.9, a little slope.
Which one are you talking about, Tegan?
Just like maybe a little sliver between like 28.
Yeah, maybe a little sliver like over in here somewhere, and just kind of estimate. So let's say I just chose 8 off the top of my head. This is 17.9. So 8's like a little less than half of that, right? So I would make it skinnier, a little bit less than half of that size. So always look at another one and compare it. If it's half of another one, if it's a little more than half or less than half. So you could say, oh, if I did have an 8, I would have to take this one, cut it in half and make it a little bit smaller somehow. Just make sure when you're creating one freehand that all the pieces make sense relative to the other ones. So that when I first divided it into thirds, we chose this one because I didn't really do a very good job of thirds. This one definitely is bigger than that one. You want to make sure that this one's bigger than that one. We want to make sure that these two are the same size. And they both should be smaller than that guy. We could argue if we wanted that maybe this one's supposed to be a little bigger and these two are supposed to be a little smaller. If we got out a protractor and we knew how to use it, we could probably figure out if I was accurate or not. But I'm just making sure that relative to everything else it makes sense. Questions about how to make a pie chart? Yes? Oh, she's playing with her hand. Okay? Now, it's not written on your notes, but it does show up in the homework in the lab. They ask for what's called a Pareto chart. P-R-E-T-O. Squeeze that in there somewhere. There's not a lot of room on this page, sorry. Maybe you need an extra page. The good news is Pareto charts are easier than pie charts. It is essentially taking the same information from your pie chart and making a bar chart instead. Instead of numbers like we had Monday for our histogram, we have our categories. We had plain, peanut, Skittles. Every once in a while I throw extra things that aren't in your notes, sorry. But it makes you be more prepared for your homework. Reese's Pieces. I'm gonna put the none on here also. Just listing my 5 categories. So I don't have to have like boundaries and all that because they're not numbers. Frequencies. Just like we did for histograms. What's my highest frequency over there? 14? So maybe I'll count by 2s. 2, 4, 6, 8, 10, 12, 14. Squeezing my frequencies in there. And then I just make a bar for each one of my categories, just like we did for histograms. It's pretty easy. Plain had 7 people. So 7 for the plain. 11 for the peanut. I'm going up halfway between the 10 and the 12 for that one. Up to the 11 there. Am I okay with what I'm doing there? Skittles goes all the way up to the 14. And the next one was a 7 again. And then I have nothing in this one, so I don't really draw any. It just kind of stays looking like that. It's just another graph that tells us the same information. If someone was doing a survey, excuse me, you're just as likely to see a pie chart in their results as you are to see a bar graph. No one's going to say which one's better or worse necessarily. Yes, ma'am.
Isn't that a histogram? Because they're touching?
Good question. A histogram, the only difference between a histogram and a Pareto chart or a bar chart is that these are numbers down here for a histogram. Like you have a range, you have your class boundaries or your midpoints for however you label it. Whether or not they touch doesn't technically matter. So I could have, if I wanted to, use the power of my eraser. You don't have to erase yours. But if I wanted to say, make these all not touch, I'm going to just make them all a little skinnier here. If I wanted to say, here's the plain and here's the peanut, I'm just making them all skinnier. So you're right, the histogram they have to touch. So I could have done that, just make them all skinnier. They don't have to touch in a bar chart. And you don't have a number line here that's evenly spaced, you're just labeling categories. So a lot of people get histograms and Pareto charts / bar charts mixed up. They all have bars. The difference is number line here versus just labeling your categories.
Do you want
Yes,
those spaced out like that, or could they be?
it doesn't matter, that was my point. They could touch or they don't have to touch. A histogram has to touch, but a Pareto chart does not. That's why I went back, I'll do it differently this time. Yes,
Does a bar chart have to not touch?
it doesn't matter.
Oh, it doesn't matter.
So the first way I drew it was fine also.
For a bar
So it
chart.
doesn't matter. Bar charts, you have all kinds of flexibility. The only one that's specific is the histogram they must touch. And you have to label that x-axis with your numbers that shows your classes from here to there, the boundaries or the limits and all that. I love that you guys want to know these subtle details, the differences and similarities. Questions? Okay there? Okay, last kind of chart we're going to do before we take our break is we're going to make a scatter plot. Scatter plots are a little time consuming. Not these other ones are quick, but scatter plots, make sure you write this down somewhere in your notes, only work if you have pairs of data. Look at that box I gave you there in the middle of page 20. Those are maybe reflecting some people. And you have a height and a weight for 5 different people. 5? Yes, 5 different people. So there's one person who's 67 inches tall who weighs 155. And there's another person that's 72 and 220 pounds. So those are pairs of data. So if I asked you 2 questions, how much money do you have in your wallet right now and how many pets do you have? Each of you would give me a pair of numbers. Then I could make a scatter plot. If I asked you only one question, it wouldn't make any sense. Or if I didn't ask the questions at the same time. Like today, I'm just gonna write down how many pets everybody has. And then next class, I'm gonna write down how much money everybody has in their pocket at the moment. I don't know which numbers go with who anymore if I do it on 2 separate days. What if you're sitting in a different place or something? So it has to be a pair of data. When you have a pair, you can make a scatter plot. And a scatter plot is essentially what you learned in algebra, where you have to plot your xy points. You have to go plot all your xy pairs on the x and y axis. So above that chart there with the height and the weight, let the height be the x's and the weight be the y's. Little review of algebra graphs. So the height is going to be my x-axis. And the weight is going to be my y-axis. And here's where we need to be a little precise. What kind of heights do I have there? What kind of numbers?
Between 60 and 70.
60 and 70? Do I want to start counting at 0? Not really. Nothing's going to happen until I get in the 60s, right? If I started counting at 0, everything would be squished over here in the 60 and 70 range. So I want to start counting at 60. What's my lowest? What is my lowest one? 67?
52 or 67.
67? Okay. I'm gonna start counting. I'm gonna start 65 even. Everything's higher than that. I'm gonna start at 65. I have to go up as high as 77. I'm just gonna rough estimate count by 5s here. 65, 70, 75, and 80. That just makes sure that all of my x values will fit in there somewhere. However you count and measure, if you want to count by ones, if you want to label every point, that's completely up to you. This must be evenly spaced. But what we do it in red, is you have to make a little slash here to tell you that this distance right here does not represent 65. It's not like this is 65, because this measurement here is 5, so how could that be 65? We're supposed to be consistent. So these little double slashes tell us that we know this part's not consistent. It really starts at 65. Otherwise, we would have had to mark everything. And same thing with our weights. What's the lowest and highest we have there? 155 up to 240. I might need to count by tens for that. Let's see. 150, 160, 170, Again, I'm just trying to make it work, and sometimes your first guess is not the best guess to make everything fit, and you just use the power of the eraser and start over again. I think I'm gonna make it fit by counting by tens. Again, everything evenly spaced from where I decide to start to where I decide to stop. I think that fits everything. And double slash here too. Right, because this distance is not 150, we're counting by tens from then on up. If you don't put that slash there, it's confusing, because when I look here, these spaces will all look like they're 10. If I'm counting by tens, how come this space represents 150? It's like it's either it's 10 or it's 150, it can't be both. So that's what that just says, don't look at anything before those lines, essentially. Now we're just plotting XY points, like you did in algebra. Is pairs. So the first one is 67 and 155. So I'm gonna go over to 67, which is roughly here. Go up to 155, which I have to stand in front of it for a second. Right about there. If I labeled it so you can see where that came from. That's x of 67, y of 155. You do not have to label every dot. I'm labeling them so that you can see where these dots came from. And then 72 goes with 220. So we'll come over here to 72, which is about here. Go up to 220. Out there. Remember the first day of class, I said you might want to bring a ruler and a straight edge. Some people really want their lines to be precise. I don't care, as long as it's accurate and legible, close enough for me. Questions on where those dots are coming from? Okay, what else do I have? 77 and 240. That's going to be up here. When I'm standing this close to it, it may not line up from where you are, but I'm trying my best. It's hard to see it from where I'm standing that close. And 74 and 195. 195 is about here. And then finally 69 and 175. 69, 175. So it looks something like that. Does yours look close to mine? I didn't label all the other ones. I did the first one, but they have to go in pairs, the x and the y, just like you did in algebra. We're going to spend a lot more time with scatter plots in later chapters, where we're going to discuss how close this relationship is to linear. How close is it to a line? Does it look like it's following a line? She says not really, but kind of, right? I mean,
Like a general.
there's a general direction. They seems to be like, following a line through here, kind of. They're definitely not in a straight line. But it seems that the taller you are, the more you weigh in general. The further out you get this way, the higher up your weight in general. Which makes sense, that's true in general, but there's exceptions. Some people are tall and skinny, some people are shorter and heavier. But in general, that seems, we'll be talking about how to determine if there's a relationship there or not. For now, we're really just making the scatter plot, plotting the points to look for a relationship. If the dots were like all over the place, like if I asked you my question about how much money you have right now and how many pets you have, what do you think the graph would look like?
Be all over the place.
All over the place. My numbers would be 0, I don't bring any money to school, 0 and 4. Because I have no money with me right now and I have 4 pets. Somebody else's number might be 32 and 0. I mean, and there's no relationship, right, between how many pets you have and how much money you have in your wallet. I don't think there is. Would be odd if there was. But we would just expect the dots to be all over the place and then we wouldn't find any relationship. So that's what the scatter plot does. It tells you if there's some kind of visual relationship on how the x's and y's are related. We good there? Okay, let's take questions. All right, so we're going to move on to chapter 3. Section 3.1, which is on page 24. Page 24. Those of you who I handed out the notes, it's just on the back of that thing I gave you today. So far this semester, we talked about how to collect data and trying not to have any bias. We talked about all the different ways you could collect the data, systematic sampling, cluster sampling, and so forth. We talked about the types of data, quantitative, categorical. We talked about how to make graphs to display your data. But sometimes we use numbers to describe our data. A lot of you have used numbers to describe data and understand it in your whole life, you've just never really thought about it. If I said the average age in this room is 20, that's describing everybody in this room in a sense. If I say the average age is 20, you know, that's around the middle. Some people are younger, older. How would I have calculated the average age being 20? If it was 20, what would I do to get that? How do I calculate an average? You did this before you met me.
Add them all up and divide.
Thank you. Add everybody's age up and then divide by however many are in here. 40 people in here. Add everybody's age, divide by 40 to get the average. And maybe it turns out to be that the average age is 20 years old. So that's a number that describes what's typical, what's in the middle. So everything in section 3.1 is describing what we call measures of center. 3.1, hopefully you corrected your notes, right? 3.1 measures of center on page 24. Measures of center are what's in the middle. The definition of middle changes though. That's why it's plural measures of center. The word average that we just talked about is no longer going to be used. We call it the mean. In parentheses, I'm going to put average right here, because that's what most of you already knew about average. So section 3.1 talks about lots of ways to talk about the middle of the data. And there's many of them. The mean is one of them, and it even says to do what we're supposed to do. What Kevin just told us. Add all the data, divide by the total number of values. So if there's 40 people in the room, I'm going to add up 40 ages, divide by 40. We're now going to be calling that the mean from now on. Not the average anymore. It's called the mean. Look at that scary formula. I love scary formulas. Get your heart rate up a little bit. We're going to talk about what this means. There's this formula over there on the side of your notes. I'm going to start with the bottom because it's easier. There's a little letter N there. N for the whole semester will represent your sample size, the number of data points in your group. So N is the sample size. So in the example I just spoke about, because there are 40 of you in here, N would be 40. Right, if I added up all 40 ages and divided by 40, I have a sample of size 40. The X's, just regular X by itself, is each of the data points. So I asked one person how old they are, this person's 18, this person's 24, this person's 19. Each of those is a different X. This funky symbol right here is called a sigma. It's a Greek sigma. And it tells you that we want to find the sum. It's shorthand math notation, number one, to scare you. Which already, I think I succeeded in scaring half of you with it. By the way, there's lots and lots of scary formulas and statistics, and I will break them down to make them not scary, or tell you to ignore them and use a calculator sometimes. But this means sum. Find the sum, meaning add. Add all the X's. So if I take all your ages, those are all my X's. So we just said we're going to add all the ages and then divide by 40. This is just shorthand for telling me to do that. Add all the data points and then divide by how many you have. Don't let it freak you out.
So what's the X with the line on it?
We read this as X bar. That's how we say it. In words, it's the sample mean. The mean from your sample. So let's say I was interested in the average age of all LMC students. I took you guys as my sample of size 40, and I got the sample mean. I would find that X bar was 20. So in this room, the average was 20. The mean was 20. So we call it X bar when we speak about it, but it represents the sample mean. I'm glad you asked. Because next to it is another weird symbol. Other questions? So this other weird symbol, this letter's kind of weird. The font on your paper is better than the way I can draw it. but I claim it kind of looks like a U and it kind of looks like an M. Do you agree with that? Its name in Greek is mu. Looks like an M, looks like a U. I think that's hilarious because I'm a math nerd. You say it like a kitten. Mu. Mu is also the mean, but it's the mean of the population. This is where people start to get confused. The notation matters. So remember I said I'm interested in finding the age of all LMC students. If I'm interested in finding the age of all LMC students, I'm looking to find mu for the whole population. But because I don't have time to go find everybody, and I have you here as my captive audience, I'm going to find the average of just the 40 in this room, which would be a sample mean, which is X bar. They may or may not be the same. I might find that the average age in this room is 20, but the average age of all LMC students is 22.9. So these may not be the same. They both refer, I was say they both mean a mean. They both refer to the mean. So a lot of people will ask me, wait, Jill, I thought you said X bar was the mean. And I'll say, yes, I did. Well, then you're telling me that mu is the mean. And my answer is, yes, it is. What's the difference? Sample and population, good. This notation over here looks almost the same. Add all the X's. Guess what capital N is?
Population size.
The population size. How many people in the whole population? The X's are still all the ages. So one of the reasons we learn statistics is it's just logistically difficult to go get the population mean. I don't have time to go find all 10,000 plus students out there, get all their ages, add them all up and divide by 10,000. That's a lot. But I can easily take a sample and take the mean from my sample and use that to estimate what it would be for my population. Are the formulas slightly less scary? A rule that you'll find throughout the semester. When things are written in Greek, like here's a mu, next time you'll see some other ones. If they're written in Greek, they're referring to the population. If they're written in our regular letters, X and N and so forth, even with the bar over it, it refers to your sample. So next time, I'll give you a preview. We'll see an S, and we'll see this weird little Greek that's a sigma actually. This represents your, this comes from your sample, this comes from your population. So a lot of times you'll see Greek letters and regular letters, and they mean the same thing, but it's just like this. Some refer to your sample, some refer to your population. We're going to break that down more next week. The Greek letters start freaking us out. They're all over statistics. Okay, so that's the mean. The next one down is the median. The median is the middle value when the data are placed in order. I actually mentioned that earlier when we were looking at our first stem plot. Remember I asked you for the number right in the middle of the stem plot? We figured out it was 30. So most important, you might want to underline this part, the data have to be placed in order. Don't just count to the middle of your list. They have to be in order from smallest to biggest, and then you find the one right in the middle. I catch everybody, every semester, not everybody. I catch at least one person every semester on the exam who give me the wrong median because they don't put their data in order. I'll give you some problems that are in order, and I'll give you some that aren't. If you don't put them in order, you're going to get the wrong answer. So let's talk about a nice little short list. Let's make up some numbers. I'm going to put them in order as I go. Here's a nice little short list of data. What is the median of that list? 10. The one right in the middle. We agree 10's right in the middle? If they're in order, which I put them in order on purpose. If they weren't, we'd rearrange them. This is the median. The number right in the middle. But look what it says. If there's no middle value, find the mean of the two middle values. That's like what we did with that other problem. I don't remember what it was. I'm just going to make up some numbers here. I know we were talking about 28 and 32 were the two that were closest to the middle.
Yeah, so we
Yeah,
should just
and-
average them, or,
Go ahead.
we should just add them together and divide by two.
Yeah, there is no one number right in the middle here, like the middle's right here somewhere, right? So we take the two numbers in the middle and find, she's calling it the average, but now we're gonna call that the mean from now on. So halfway between 28 and 32, we add up however many numbers we have. Take that answer, divide by 2. You'll end up with 60 divided by 2, which is 30. This is the median. So you'll be given a list of numbers, maybe like this, they'll be longer. And you'll be asked to find the mean, find the median. How would I find the mean of this list? I didn't hear you said. Somebody said something. Who was that?
It's me.
Oh, I didn't hear you said that.
I'm not sure if I'm right. So
Okay.
all of them?
Add all of them. If we wanted to find the mean of this whole list, we would add all these numbers up
And then divide by four.
and divide by 4, because there's 4 numbers in our list. That's what that formula was that we were talking about here. If we want to find the median, we just know to find the number in the middle. Either just grab the one in the middle, if they're in order, or average the 2 in the middle, and find the mean of the 2 middle ones. Be careful, because you're going to get confused, because both of these are measuring what's the center of the data. The word center is really wishy-washy here. Which one's a better descriptor of the data? It's hard to say which one's better. It depends on situation to situation. In this case, the median is 30. Let's find the mean of this one. Can we find the mean of that set? Let's find x bar for this set right here. 6 plus 28 plus 32 plus 70. I'm hoping somebody has their calculator out. I can't do that in my head. 34? Got people agreeing with her. I heard somebody else go, what?
33.
33? Did we round? They add up to, let's see, what do they add up to? 60, 136 divided by 4? Is 34?
Yeah.
I'm hearing 34. Make sure you add first, then divide. So this is a measure of center. And this is a measure of center. With this short list, we could sit here all day and argue about which one's better. But we're just kind of describing what's typical. And what's typical is if you spread them all out evenly, everyone's around 34. This is saying that exactly half of the people are older than 30 or younger than 30. There's not only one way to talk about what's typical. The next one down here on your paper is the mode. That's also used for what's typical. That's the number that shows up the most. It shows the most often. I don't have a mode in any of these short examples I just made because there's no numbers that repeat. The previous problem we did with our stem plot earlier had like a whole bunch of 6s, I think, probably more than anything else. I think we had like 3 people that were 6. We'd have to look back at it. But that would be the mode of that one because that number showed up more than anything else. Imagine if you walk into a kindergarten classroom and you took everybody's age and you've got this person who says, I'm 5, I'm 5, I'm 5, I'm 5, I'm 5. Oh, look, here's a 6-year-old. And I'm 5, and I'm 5, and here's a teacher who's 43. She's not a teacher there, right? If we averaged and found the mean of that data, that wouldn't be very typical. Because that 43 would kind of affect the mean, right? We found the mean, we would get that it's probably the average age in there is 8 or something. Or nobody in there is 8, right? So it doesn't make sense to take the mean there. The median would make sense, because if you put them all in order, you'd have 5, 5, 5, 5, 5, 5, 5, 6, and 43. And so 5 would be in the middle. So the median would make sense. And the mode would make sense, because the mode, the 5 shows up more often. That describes what's typical. So depending on the situation, sometimes the median makes more sense, sometimes the mode makes more sense, sometimes the mean makes more sense. It all just kind of depends on what you're doing. There's a lot of times when we don't use the mean, and that would be a good example, because it throws off your results. If I found the mean in that kindergarten classroom, make it a really small class, just in the interest of time. A very lucky teacher only has a handful of students. Here's the class of how many students, and then there's the teacher. Someone grab their calculator for me and tell me the mean of that list. It's my kindergarten class here. I've got 1, 2, 3, 4, 5, 6. I got 7 5-year-olds, a 6-year-old, and a 43-year-old teacher. Ten and a half? We agree with her? She added them up, divided by, I don't even know how many numbers are there. Are there 8 numbers there? I don't know. She could be wrong. I'm waiting to see if someone agrees or disagrees. There's 9 numbers? Oh, so maybe it's not 10 and a half. Speak up. She's willing to admit she's wrong.
9.33.
9.33? Someone agree with that?
Yep.
You got outvoted. It's okay. We learned from our mistakes. 9.33. This is where if the rest of you hadn't spoken up, I would have left it 10 and a half. She and I would have thought she was fine. And then later on, someone would say, Jill. Poor people watching the video going, where did they get that? Gonna correct it for the people watching the video. 9.33. The average person in that room is not 9 years old. There's nobody 9 years old in that room. So the mean in this case is not very helpful. What if the teacher was, she's real close to retirement, she's like 64. What would happen if she was 64? The mean would go up even higher if she was 64. What about the median?
5.
The median's 5. The number right in the middle is 5. Even if there's 2 numbers in the middle, they're going to average out to 5. How many numbers do I have here? 9. So 1, 2, 3, 4. This one's right in the middle. Right? Is that right in the middle? Yeah. So my median is 5. My mode is 5. Turns out they're the same. Both of those are better descriptors of what's typical in this classroom, like better measures of center in this case. Outliers, you're going to see that in your homework. Outliers are numbers that are way far away from the other ones. They don't fit in with the rest of the group. This teacher is an outlier, obviously. The outlier affects the mean, but doesn't even affect the median or the mode. Doesn't affect it at all. A good example of where you'll see the median used instead of a mean, because most of us here averages and are comfortable with that, is if you ever look online, say like housing prices. If you look at housing prices, they almost always give you the median house price, not the mean house price. Same with salaries. Because imagine if we were talking salaries, and I asked you how much you got paid per hour. I would assume, I don't know what you all do for your jobs, but I'm going to assume that most of you, a lot of you probably have minimum wage jobs. Maybe some of you moved up a little bit and are making in the teens. Maybe there's someone who makes $30 an hour. That's a pretty nice job. And then I'm also going to ask Steph Curry how much he makes per hour. I don't even know. I'm going to guess what that might be.
Probably like 500,000.
500,000 an hour, maybe? We'll go with that. It might be a little high. Maybe it's only 50,000 an hour.
Yeah,
We'll give him 50,000
Well,
an hour.
that's not the game.
Yeah. Yeah, depends on his game. You can include practice. He maybe doesn't get quite as much per hour. But this is all of our hourly wages. If we wanted to add those up, find the mean, we'd be all feeling pretty good about how much we make if we really all got the mean. And instead of with us each getting our individual salaries, we're just going to change it and make sure that everyone gets the mean. The rest of us are now really happy. Someone's already calculating that now. Anybody do the mean already? I could calculate this going, I assume someone's doing it. We all agree that 50,000 is going to mess up the mean, just like the kindergarten teacher over here. So the mean is affected by outliers. It doesn't make sense to talk about that the average salary is, who's done it now? Someone's done it, I know. There's always somebody who just wants to do it while I'm talking. Nobody? Someone quietly calculate the mean, let me know when you've got it. I can do the median. That would be this one. Typical in this room, $13 an hour. Half the people get less than 13, half the people get more than 13. Did you get it? Good try. So the median is 13. The mean, someone's gonna tell me eventually. What's the mode?
10.
10. By the way, if there is no mode, you just write that, no mode. If there's no number that shows up the most often, but there is no mode. Because more people get 10 than any other number. And the mean is, who got it?
It's 7,000.
Go ahead. We'll see if we agree. 7,000.
7,155.74.
7,4?
1.
7,1? Is that what you got too, Lexi?
Yeah.
On average, we each get like $7,000 an hour. I like this job. I'm feeling pretty good about this. Sometimes the average makes no sense because those outliers do exactly that. Housing prices are the same thing. If you were talking about housing prices here in Contra Costa County, there's houses that sell for $300,000, $400,000, $500,000. There's a whole bunch in the probably like the $400,000, $500,000, $600,000 range. But then there's one house that's much nicer on a huge plot of land, it's part of a farm, and it's gonna sell for $3 million. So all the other houses are, $500,000, $400,000, $500,000, $600,000. Then there's this $3 million house. If you average that and say, oh, the typical house in this county is, in the 800,000 range, that's not true. We talk about the median because most people want to know, what can I afford? If you told me it's 800,000, nobody would show up because it's not the middle. You want to know, oh, some are lower, some are higher. So the middle or the center changes based on what you're trying to find. Okay with the first three? The last one there is the mid-range. Halfway between the smallest and the largest, there's a weird space on mine, there probably is on yours too. Halfway between the smallest and largest data values. Let's use my example over here. Here's the smallest, here's the largest. How do I find the halfway point between those?
Add them and then.
Add them up and divide by 2. It's another mean, really. So the mid-range in this case would be 10 plus 50,000 divided by 2, which is, I think, 25,005. Is that right? Someone help me out. I'm doing math in my head. Thank you. She's like, yep, she did that. So these are all different numbers that describe what's typical of these hourly wages, if I could speak. We could say $13 an hour is typical. We could say $7,155 an hour is typical. We could say $10 an hour is typical. We can say the 25,000 and some change is typical. In this example, because of our outliers, what's typical gets really messed up. It gets affected by the outliers here, on the mean and the mid-range. You'll see a couple questions with your online homework that say, which of these measures of center are affected by outliers? This is like the worst. I don't know who uses mid-range for anything. It just doesn't make sense to me. I understand how to calculate it, but I can't come up with an example of where it's a really good measure of center. I have to do some research on that. Because it just takes the two extreme values and ignores everything in between. Yeah, what if I listed up somebody here too, like if somebody didn't work, it would be a 0. Average, but I mean, so it would change everything. Okay, middle of the page, 24, the round off rule. Online, it will always tell you where it wants you to round. But sometimes the textbook, if you're like checking your answers in the back, they'll round in places, like how do they decide where they're rounding? We always carry one more place than the original data. What that means is that, these are all whole numbers, for example. So when I find the mean here, see how we went to 7155.71? We would have just gone to the 0.7. Let me erase that. I'll remind me. One more decimal after whatever the original data was. If everything had 2 decimals, we would round to 3 decimals. You always just go one more. That's the round off rule. I'm not real picky about it. I will tell you where I want you to round. The computer will tell you where it wants you to round. But sometimes if you're checking the back of the book, how they know to round there? It's one more than the original data. Last thing. Okay, questions before I go on the last example. Of all those different things. Mean, median, mode, mid-range. Your homework will give you a list and ask you to find all of those, talk about which ones are close or different and so forth. If you have a frequency distribution, like the one at the bottom of page 24, the same one we saw, I think it was last time, when we were talking about coming up with histograms and finding class midpoints and all that. We want to find the mean price of these houses, ones we decided weren't in this county because they're all fairly inexpensive. And we have houses in the $80,000 range up to $265.9 thousand. What were the prices of these houses? Let me ask you a different question. How many houses are in this table?
$28.
32, 22, 28?
28.
How are we getting that number?
We added up all the frequency.
Add up all the frequencies? The frequencies should add up to 28. So there's 28 houses represented in this table. So if I wanted to find the mean of those 28 houses, what would I need to do? I would need to know the price of each house, add up those 28 numbers and divide by 28. Do I know the exact price of each house? I'm out of luck. See the problem? I don't have 28 house prices. How the heck am I supposed to find the mean? What'd you say? So we're gonna use the midpoint. We're going to assume that every single house was the midpoint of its class. So we found the midpoints last time. I'm not gonna create them all over again. I'm just going to list them. If someone could flip back to that page to help me, that'd be nice. I'm gonna list the midpoints. I'll put it here. We have 2 minutes. I got this. The midpoints were like 74.45, something like that. I'm guessing. Is that it? 79.45? What is it? 0.95? I'm getting my boundaries and my midpoints mixed up. Tell me again, Crystal. Midpoints. Flip back to where you see the same table.
9.5.
Thank you. What's the next one?
10.5.
Keep going.
Yes, right, yes.
You didn't write the rest of them down?
No, I just added 31.
Want the midpoints or the boundaries?
Midpoints.
Those are the boundaries.
Oh, good thing we double checked. Midpoints. It's all right.
Is it 95.45?
95.45?
126.45? 157.45?
Keep going.
188.45? 219.45? 250.45?
Okay. You good now, Crystal?
Yeah.
Okay.
I just put the wrong section.
That's all right. So those are our midpoints. So we're going to assume those 2 houses in the first class, we're going to assume that both of them were 95.45. So one of them was 95.45 and the next one was 95.45. And then I'm going to assume that those next 5 houses in the next class, the 5, I'm going to assume there were 5 that were this price. So I have 2 of these, I have 5 of those, I have 7 of these. So then I would actually have 28 numbers. I don't want to list all 28 of them, so the shortcut is, I know we're out of time, hang on 1 second. The shortcut is to say, I'm going to multiply this by 2. I'm going to multiply this by 5. I'm multiplying by the frequencies. I have to make sure I put the right frequencies in here. Multiplying all these. Because that's essentially adding up 2 of these, adding 5 of those, adding 7 of these. I'm going to multiply all those.
Add them together.
I'm going to add them all up. And then what?
Divide by
Divide by
20.
28, because there's actually 28 numbers here. Then divide by 28. Multiply by your frequencies, get all those answers. It's time consuming and we're out of time. Add them all up, divide by 28. When I see you next time, we learn our calculators, I'll show you how to do it in a lot less time. We'll do that next time. I will see you in the lab if if not, I will see you next week.